So, very hearty welcome to everyone who have tuned in into this meet. We sincerely feel honored to have a chance to speak at this virtual showcase. Our team Nirmaan Hyperloop started back in 2018, and since then, we are now a team of 40 plus students from various domains working towards bringing the Hyperloop to reality. Talking about our achievements, we have gotten quite a few. The first one being we were among the top 50 teams at the tunnel boring competition. We were also the first in Mumbai, the city that we currently reside in, to build an entirely in-house linear induction motor. We have also been featured in multiple newspapers, including the Times of India, that is the national newspaper of India. Uh, Now, with that, I would like to call upon Mr. Anjani Kumar, who would take us through the propulsion part of our pod, as well as introduce us to our pod as a whole.
Yeah, so thank you very much, Steve. Hello, everyone. My name is Anjani Kumar Dubey. I am currently the propulsion member of Nirmaan Hyperloop and also a third year mechatronics engineering student. So, coming on to the pod Praveg. Now, we all might have heard the name Praveg, but why Praveg? So, Praveg is a Sanskrit word that is synonym for speed. So, that's why we have named our first pod that is Praveg. The length of this pod is 1.7 meters and the width is of 0.47 meters with the height of 0.5 meters. So as we saw the dimensions, let's move on to the weight of the pod. So the total weight of the pod is 155 kg. As we can see the dividing of the division of the weights. So the we can see the battery consumes 45 kg on the pod. The limb is of 35.1 kg and the support structures are of 9 kg, and the other distributions also. So for propelling this huge pod, we need a better propulsion system. So let's move on to the propulsion system of our uh, Nirmaan Hyperloop. So the second Laghu Vajra is a second iteration and a first successful one. So Laghu Vajra was basically made for study purposes and for understanding and for proving a concept. So Laghu Vajra is a 24 slot and a three-phase, a two-pole linear induction motor that has a rated voltage of 415 volts, a rated current of 3 amperes, and a output power of 1.5 kilowatts. The mechanical dimensions of this limb were 310.5 millimeters of stator length, 87 millimeters of stator width, and 26.25 millimeters of stator height. So now, as this was made for the proof of concept, we have also done the testing of this Laghu Vajra in our nearby campus of IIT Delhi, IIT Bombay. So during the testing, we learned many things, and we got to know about the how to move from simulations to the real world and the reality of building lean induction motors. We have tested it on the 58 volts of voltage and 2.5 amperes of current, and which gave us the output power of 1.5 kilowatt. With this learning and which helped us a lot, we made a final iteration for 2023 of DSLM configuration, that is Vajra. So Vajra is a 24 slot, three phase and a two pole linear induction motor. That is the final iteration for 2023 that we are going to have in a pod. This linear induction motor also has the rated voltage of 415 volts, but it has a rated current of 52 amperes, which gives us the output power of 33.33 kilowatt. The mechanical dimensions of this DSLM configuration are 59, 59 5000 and 5900 500, sorry, my bad, 594 millimeters, a stator width of 55 millimeters, and a stator height also of 55 millimeters. The weight of this DSLM configuration is 35.1 kg. Now, moving on to the simulation part of this Vajra, we had did this simulation on the 50 hertz frequency, which gave us a scale down force of 3.3 kilowatt. For the desired power, that is 33.33 kilowatt, for propelling the 155 kg Praveg, we are doing the number of iterations at different frequencies to get the desired design output. Now, for a better propulsion system, not only a better linear induction motor, but also we need a better controlling systems. So for controlling, we are using the VFD, that is a variable frequency drive. Uh, before that, uh, before moving on to the controlling of the limb, let's see the quick comparison between the Laghu Vajra and Vajra. Why is Vajra better than the Laghu Vajra? So as mentioned earlier, Laghu Vajra was basically for understanding and for proofing of concept that we are going on the right path, we are heading towards the right goal. So Laghu Vajra had a power output of 1.5 kilowatt, whereas Vajra, that is going to propel the pod, it is having the power output of 33.33 kilowatt. The rated current of the Laghu Vajra was 3 amperes, whereas of Vajra it is a 52 amperes. As we can see also, there is a lot of changes in the mechanical dimensions, as the length of the Laghu Vajra was 310.5 millimeters, whereas that of Vajra is 594 millimeters. Also, the height of the Laghu Vajra was 26.5 millimeters, whereas that of Vajra is 55 millimeters, which gives us a better electrical conduction and a better force for propelling the pod. Now, moving on to the controlling of the linear induction motor, we have the variable frequency drives. So variable frequency drives is basically a drive that is used to control any AC motor. So the current requirement for the variable frequency drive is between 5 amperes to 7 amperes, based on the average power of both the limbs and the voltage of the VFD. We will connect the VFD between the inverter and the limbs. That would from the battery, the power would get inverted, and that would go into the VFD, and then VFD would give that power to the linear induction motor. Also, the VFD would be connected to PLCs and other sensor systems, which would help us to control the pod in a better way. So, for the sensor and control part, I would like to call upon Ankit Maurya. Handing over
Uh,
to you, Ankit.
Thank you. I am Ankit More. I am part of the software team at Nirmaan Hyperloop, and now I'll be presenting the sensor and control system part. So first, let's see the state diagram. So the pod, when we start the pod, so basically first it goes through some checkups. So basically we check whether all the sensors are up and running and we are able to read them, and also that the the communication between the pod and the control system is there. And upon passing those checks, the pod is ready for its run. And upon receiving command from a control system, the pod starts its acceleration, cruising, and deceleration stage. And when the pod comes to a stop, it goes to the ground stage. During this run, we have logged all the data from all the various sensors which we have on the pod, and using that data, we are performing system diagnosis on the pod. And and during the run, if anything goes wrong, for example, if the sensor stop working during the run, so the pod will immediately go to the failure stage where the brakes will be applied and the pod will come to the ground stage. Now next we have the system architecture of our pod. So the first we have the input layer. And so we are using various sensors to measure various aspects of our pod when it's running. So first we have the triangular sensor. So basically it's a distance sensor, specifically a laser distance sensor. So we have mounted 4 of this in the front of a pod and 4 in the back. So basically we are using this sensor to measure the elevation of a pod from the track, and also the gap height between the pod and the vertical part of the I-beam. Next we have the temperature sensor. So we are using this temperature sensor to measure the temperature of a linear induction motor and the other electrical component on the pod. After that, we have the pressure sensor. We have mounted this pressure sensor on top of our pod. We are using it to measure the pressure experienced by the pod when it's running in air and also in vacuum. After that, we have the voltage and the current sensor. So we are using this sensor to monitor all the electrical component in a pod. After that, we have the navigation sensor. So basically, we are using this navigation sensor to detect reflective strips. So basically, the track on which a pod will be running have reflective strips after every X interval of distance. So using this sensor, we can detect those strips when the pod is running, and based on that, we get to know the actual live location of our pod on the track, and also we get to know how much percentage of the part the pod has covered. After that, we have the IMU. So we have placed this IMU at the center of gravity point of a pod. So this IMU is providing us with the uh, gyroscopic and the acceleration of our pod. After that, we have a Hall sensor. So basically this Hall sensor, we are using to measure the magnetic field produced by a linear induction motor. After that, we have this ultrasonic sensor. So it's a basic ultrasonic sensor which we are using to measure the distance between our both brake clamps. So with the help of this sensor, we can detect whether our brakes are open or they are partially closed or fully closed. After that, we have a camera in front of a pod with which helps we are streaming a live feed in a control system. Now the next part of our system architecture is the processing layer. So all the data from the sensors is fed to the processing layer. So in the processing layer, we are using an PLC. So basically, PLC stands for Programmable Logic Controller. So the particular one which we are using is from Phoenix Contact, and the model name is AXCF2152. So this particular controller is really fast because it has two Cortex A9 cores which are running at 800 megahertz, and because of this computational power, uh, this particular PLC can send and receive command to our control software under a millisecond, even if multiple devices are connected. This is a little block diagram for a PLC. So basically, all the data from the sensors, raw data from the sensor, are fed to our PLC. Whether the PLC does the processing on those data, and based on that, it performs an actuation command. For example, the PLC will be controlling the solenoid valve for a pneumatic brake system, and also it will also be controlling the VFD, which is producing that three-phase output for controlling a linear induction motor. Now the next part of our system architecture is our control is our output layer. So basically our output layer, which is our software which we have developed in-house, is communicating with the PLC over the Wi-Fi network. So this is a little demo of our graphical user interface. So basically on the left side we have the crucial information, for example, the velocity, acceleration, propulsion, pressure, and all of that. And on the right side, we have all the raw data from every sensor. So we have developed this particular user interface using Python, specifically the PyEdifice library. And for the communication part with the PLC, so the PLC which we are using is from Phoenix Context. So they have their own proprietary Python library for the communication part, which makes our work easier. And also all the communication happening between the PLC and the software is encrypted using the transport layer security. So it's safe also. After that, we have the safety layer. So it is very important part of our system architecture. So for example, when the pod is running, if anything goes wrong, then the emergency stop is applied. So the condition for applying the emergency stops are that the communication is bugged or improper. For example, if the communication between a PLC and a control system breaks during the run, so the PLC will automatically apply the emergency stop sequence. After that, the next condition is that uh, any sensors goes offline during the run. For example, if the pod is running and we are unable to measure the pod temperature because the temperature sensor has gone offline, in that case also we are going to apply the emergency stop sequence. After the next condition is that brakes are not working properly. So as we talked, we have this ultrasonic sensor which can measure the brake's current position. So for example, if you have given the command to brake, to close, and with the help of that ultrasonic sensor, we can actually detect whether the brakes are closing or not. And if we detect that it's not responding as it should be, in that case, we will apply the emergency stop system. The next condition is the propulsion system is offline or not responding in time. So with the help of that Hall sensor, we can detect the magnetic field produced by a linear induction motor in real time. If the magnetic field which is produced by a linear induction motor doesn't match what it should create. For example, if I've given the command to the linear induction motor to stop, but with the help of that Hall sensor, we can still detect that it's still producing electromagnetic fields. So in that case, we will apply the emergency brake. And the last condition is that the team detects anomalies. So our control system is saying that everything is perfect, but the team can see that something is not quite right with the pod or the system. So in that case, the team can use our control system to apply the emergency stop. So next part of our system architecture is the actuation commands. So we have a little demo for that. So here on the right hand side, we are running our control software on the laptop, and on this black board, we have the PLC. So this PLC and a control system software are basically communicating over the Wi-Fi network. And upon receiving command from a control system, the PLC will actually give the actuation command to this solenoid valve, which will extend and retract our pneumatic braking system. So here, so when we press the stop button in the control software, the brakes get applied, and when we press start, the brake get released. So before we end our presentation, I would like to thank our sponsor for supporting and helping our team, without which we couldn't have reached this point. Thank you. So we are done with our presentation and we are ready if any questions are there.